three were in the same room.
Probably get. Something like 0.02. So I don't know. So just use the more massive, or I just use the massive box sample we collected. And converted that into moles and then moles of the container and divided by
2 to 1 for each person.
When you get migraines behind your eyes. Come on.
Or I don't know. That's just what it said on the board. It said like permanganate to oxalate was 2. On the first like
I didn't think an initiative.
it's kind of in the
Okay, thank you for coming.
my 32.
Better.
Always.
Just sacrificing your time for stuff that is boring.
Oh, and take over more time. Hey, research, this should be on campus.
It is the future of the research. So, it is stuff that is in class, right?
Oh,
And then you see there's a few additional factors and people do it all together and configure.
No. It's like,
I think it is a YouTube video that was the part for Kyle was already covered in the class. We will do it on so I will show something like slides for these two gentlemen because they agreed to take the hardest part, and then for the rest we'll bring up meta stuff and bring the whole session. But I'm committed. So the most important is you're discussing to find eigenvalues, and then one makes a segment, plot them all, right? And density of states is nothing but the just exponential, Gaussian exponential centered at the energy of specific energy. So, and this is density of states, right? We will do it live. I just want to cover as much as possible the quick presentation style, and then we'll go to hands-on. So, dimensionalities. When you will be, if Garrett doesn't run for 30. Well, even if he does, you'll run a campaign project. So when there will be time for projects, hopefully, some of you may decide to be closer to reality, and the larger number of dimensionalities, the closer project is to reality. So the one-dimensional wave packet for three-dimensional space is a little iffy, right? Although it is very helpful, it is continuously used for many problems, but 2 dimensions are better than 1, and 3 would be even better. So how to add additional dimension? Here are the eigenstates for 2-dimensional oscillator. They just quickly go in one after another, and you see there are pluses and minuses, right? Positive and negative, and they have this fading out both in x and y dimensions, and there are like quantum numbers in both of them. If one would start is an article. It's not that I'm speechless. If one would start initial Gaussian wave packet in 2 dimensions, then it will. You see this dense black fringes show the. On my screen, it goes much better. There is a delay because of the big screen. So if you can see, here is much more spectacular. And there are links that you can follow and play it on yourself on YouTube. So there are 2 types of ISO lines. One is black, and it is basically concentric circles. Another is blue, and it goes up and down. So blue is wave function, black concentric is probability. It is 2-dimensional, and then it changes phase, and at the same time the center moves forwards and backwards. And there was a little dashed line that plots a trace. Who and why needs 2-dimensional? It's beyond my goal right now. I'm just covering technical stuff. But if you have, for example, your predecessor Eva, there is a reaction of once the species as a whole approaches the catalytic center, then breaks and departs, and the distance between parts of the species disconnects. So it's 2-dimensional reaction, and it's already done. And you saw the movie here went through very quickly and was even not showing all the things. I do have the same movie being prepared. I'm running this code that has been sent to you as well alive, and to accumulate this movie, it would take to run it overnight and maybe longer. So we may try to run it, but be patient. If you and the movie without specific tricks will be on itself like 12 minutes. Here it is each 10th or each 100th snapshot to have it more continuous. When you will run the code, you will see there are different aspect ratios, but let's return back to the slides. So you have seen the movie working. There is also a link of one of the students from previous year, and it is not Eva. It is a auditing person, same as Ifani. There was Patricia last year, and here is a recording of her talk. I will not run it whole. It's like 8 minutes, but she tries to explain her best how it works and what it does. There's certain level of success, and we are not going to play. There will be movies about each of you later. So what is important in this in the code, and it is already transmitted through email. Their main part of the code that we all are using one-dimensional, that we represent wave functions as a vectors and operators like Hamiltonian, evolution operator, momentum as matrices, right? As an object with 2 indices. Here is a paradox. If you have 2 dimensions, you have momentum for X, momentum for Y. They both are square matrices. but then how do we combine them? Or there is a wave function with amount of grid points is about 200. Here, to speed it up, it's like 50 in each dimension. Otherwise, it will be too long. Like 50 grid points in X, 50 in Y. Total, it gives like 2,500 square matrix if you want to map it, right? But then how to match this setup with our original setup that and paradigm that any wave function is a vector and any matrix is any operator is a matrix. How do we convert this square map of two-dimensional wave function onto a vector? It is not my frivolous whimsical. It is a formulation of quantum mechanics that operators are matrices that we diagonalize. So we need to convert everything into the form of square matrix. How to do it? So the main thing, absolutely main part of this code is a concept of super index. So basically, if you understand and you can reprogram and explain this equation, the rest is rolling down in a natural form. So suppose we do have this wave function with x and y grid point, maybe I and j. And then we increase and we want to save it as a big vector, which should have the same number of elements. So like 250 here, 2,500 here, and 2,500 there. So the question is, how do we map it? So we go din 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 din. Please give a blue color. No, it doesn't give. So we go scan points in rows and columns, and here we need to go just one direction, right? So here we have indices I and j, and here we have big index. If you do know the size of this rectangle, if amount of points here is k max, then each time we continue our motion from one side to another, we stop incrementing index j, and we make a big jump in the overall big index, which is equal next value of index I times the size of the box. Like if I have a fiction with several volumes, I count pages, but then I take the next volume and start counting pages from the over again. Okay, so and then this product psi is a wave function which is two-dimensional, and this big psi depends only on one index. So we convert mid-size square matrix into very large vector. Okay. If anyone decides to do it in three-dimensional, then this conversion will be a little longer. Right? It's also possible, but let's not waste time right now. So I'm erasing. This slide does show how to prepare initial condition. I'm not pretending to show the complete picture, but just giving it a little overview. So if you have this wave function along x, along y, and we set up initial position, initial momentum, and then we set up a product of this two wave functions, where one is conjugated and another is not. It will be a matrix that correspond to this wave function. But then we convert this product from two indices into big psi with one index. And then it will be used as initial condition for the dynamics. So the conversion between super index and little index is needed several times. Forward. So if we have predicted by some computations the wave function at certain time of a certain eigenstate as a vector. We need to convert it backwards into two-dimensional map. And then in the previous cycle, we just invert the order. So we assign value from, so it is the same conversion procedure, and then we assign the element of the one-dimensional array into the element of two-dimensional map. So we can confidently convert between vector and matrix forwards and backwards. I've already learned that I shouldn't use the word that something scares me. No, I'm brave and happy to look on these equations. They are easy like snap, and I just get elevated mode. So here there is, I already mentioned number one main equation. Here is a main equation number two. So you probably recognize that there are two super indices because we want to deal with operators. And operators, if wave function has a size of k max 50, then the big wave function will have a size 50 by 50, 2500. And super matrix that will govern evolution of this wave function will be 2500 by 2500, k max to the fourth power. So it's like we need to convert from 4 indices to 2 super indices. This stuff with indices seems natural, but then we need to form big Hamiltonian with a method 3 with 2 big indices. And here is the only non-trivial equation that I really want to speak, and the rest then I can complete and then go to practical details. We do need an identity operator that will keep certain pair of indices untouched. So total number of indices like I1, I2, J1, J2. For I1, J1 for X dimension, I2, J2 for Y dimension. And we know how to create operators that will make conversion between wave functions related to certain dimensionality. So we want to use this knowledge. We want to apply, for example, momentum operator or kinetic energy operator or total Hamiltonian operator to a certain degree of freedom. But when we apply our known stuff, we should keep another degree of freedom unchanged. Therefore, it has here Hamiltonian 3, which we defined before, kinetic energy, in respect to X dimension, I1, J1. And then in respect to other 2 indices, it is an identity operator. It is defined here. So it's like matrix with ones on the main diagonal and zeros elsewhere. But now we need to make an operator that will act on the other pair of indices on other dimension. So it is again the same Hamiltonian, but now it acts on Y dimension. It depends on I2, J2. And in respect to first 2 indices, it is an identity operator. So if you combine them together, it will be an index with, it is a procedure to convert from 4 to 2 indices. And if we, Hamiltonian is diagonal in terms of this stuff, so it's a little easier. We do additional thing only if we go along the diagonal of this supermatrix. So if this stuff is done correctly, you saw that the dynamics goes reasonable, and one can justify it by theoretical predictions that it gives what we need. I think I need nothing more. Oh, yeah, here we return back to this subject is between Garrett and Kaiden. It is a eigenstates for two-dimensional stuff. So we play the diagonalization of this big Hamiltonian. Now this stuff goes to Curtis. In everything we do, you want to do movies, right? So we open a channel to store the movies, open, and then we scan through orbitals, assign to a certain variable the orbital from the list, the energy from the list, perform conversion from one-dimensional to two-dimensional, convert wave function into probability, and do the surface of this two-dimensional map. And then we do get frame, write it into the video channel, and when all cycles are finished, we close the channel. And then it gives, I'm going to jump back. It gives this video. We just plot eigenstates one after another. Okay. I think I did show everything I wanted. Now we just need to play with hands-on. So everyone who is curious is welcome to run the code like 2D Patricia. Patricia is not the name of the code, it's the name of the student who was running and developing. It's like a hello Siri, hello Patricia. But the first part where it gives away eigenstates will complete in a reasonable time. The one that complete the whole dynamics is not possible to run and wait until the end during this class. So it would be prudent just to, if you decide to run it, just run and stop, and then rerun it at home when you let your computer work and you as a person go asleep. Okay. Any questions? Oh, please.
I'll ask the questions.
Okay.
Right now.
I'm going to stop. It is running for about 2 hours, but it has completed about 2 oscillations for forwards and backwards. And you see one can just look on it from different aspects. Now I did stop it. It doesn't move anywhere. So it's potential energy surface with like harmonic and Morse in one and another, and it shows this different representation of wave functions, and then this orange and red stuff are projections of probability distribution on the axis. Okay, I'm going to close this stuff. If I would go through the actual code, it would kill the program of the class. It's doable. I'm very enthusiastic, but it would take too long. So I'm going to close all graphical windows, and then we will go to the. Everyone is invited to. So I need to clear. To do the stuff for two-dimensional, not for one-dimensional oscillator. Okay. The code works in a very similar fashion as we had before, and it just shows oscillation of the wave packet in the harmonic potential. To reproduce this dependence by pen and paper equations will be a goal in the class for another 2 weeks, but we can look on it right away. So it just goes forwards and backwards. Let's see, what do we need to do here? Open. So I was removing comment in the line 64. Now this defines the quadratic potential. So V is certain rigidity times elongation squared, and this 40 is set of the equilibrium position. The rest of the code is the same, and if one wants to find eigenstates, one just run this module orbital. And in fact, I copy pasted it inside the code as well, which you may do either one, what you prefer. So this couple of lines up from 172 to 197. Okay, now let's look for visual. The order doesn't mean much, but I'll just continue here and then return back to reverse things. So visualize real and imaginary parts of the wave function. Hello, Ifani. How are you? So figure, maybe I think we were doing it last time, right? So plot real size 3. Hold on. What imaginary size 3. So real and imaginary part, and if we do plot 3 x real imaginary we'll have this spirals, because wave function has real and imaginary parts. So we can visualize real and imaginary parts, and I believe in the sign up page, yes, this little thing here, it is real and imaginary part of the wave function for relatively high momentum. Okay, visualize potential and probability distribution. I think hold off because I do not want hold off. I think the variable v is where potential is saved. So if you run the code without, and you lost track what is defined as potential, you just plot v and you see what it is. Potential probability distribution. I think it is prob, which is nothing but psi. If you do absolute value of psi, and then you take a square of it, it will be the same as prob. Let's do it and then find where it is defined. So you see, it shows the same prob 3 and absolute value squared. Is this sufficient font, or you prefer a little higher? Anyone wants larger font? You all can see from distance. I'm jealous. Okay. Let's look inside the code where are this command. So we should have it in the yes. So we have g tau times propagates past to the near past to near future. So the variable psi3 is updated any time we come through the loop, and then prob3 is updated probability distribution, and then it is plotted over and over again and saved into movies. Why is there three of them? Well, because we have method 2, method 3, and there is one more method that I suggest we skip because it deals only for, it's important only for free space. It is propagation in momentum space. This E, tau, and phi is wave function momentum space, and in order to plot it, it is converted by inverse Fourier transform from momentum space to position space. I don't see any practical reason for this class to do it, but here is the answer. Yeah, here is how it is defined. So K is momentum operator, and it is free space without potential in using momentum as independent variable. Okay, what is next? Visualize any observable. Now it gets connected to the question to Spencer. Visualize any observable. So there is a part of the script that declares observables that will be saved along the trajectory. And there is a, now what I'm telling is equally important for both Anna and Curtis. So here is the, I wouldn't say challenge or problem, but at each point of time, we are computing an instantaneous value of the an instantaneous value of an observable, and we'll go through the way how it is computed. But when the code has completed, we do want to plot this observables like expectation value of position, expectation value of momentum, and others, right? So we need to put value of observable at each time step. There are two ways. One is to just make a point on a graph each time it comes through, or another, a little more long-term working, to accumulate all data points into a single data set, into like array or into a file, and then plot on demand when it is needed. So we do generate one point of data, and we need to create an array. How it is implemented? Not all, but several of expectation values, excuse me, starts with AVE for average value. The area closer to the end of main cycle basically write about last 3 dozen of lines before the end of the cycle, before this pause, deals with accumulating expectation values. Okay, let's focus on this one. What does this equation stand for? How to interpret it? So we do have expectation value of x. We know that it should be psi star x psi dx, but since x is diagonal element, we can replace it just for simplicity psi star psi, which is probability times x dx. So this is what we do. So summation of x as operator times probability distribution. And since we have the square root of dx in the initial definition of the wave packet, summation will immediately give the result of integration. So this AVG3 is expectation value of position, so average position of the wave packet at given time, at time t. But it is only one number. Now, we do need many numbers. We need a trajectory, how the center of the wave packet evolves over time. So we do this averages, many of them is what it was before, and we increase the length of the array by one. We could write it in the opposite way, in the form like AVGS3 equals open bracket AVGS3, and then it's so this is 3. This is not closed bracket 3, and then in the next line to write AVG3 and then close the bracket. So we were doing it when we were creating arrays at one of our first meetings, right? So if you have an array and then you put additional number, you expand, array becomes longer, right? So let's check if this all makes sense. I'm going to erase this little comments. And double check if I'm going to the command line, and I will request plot x along x and AVGS3 along y. Doesn't want, okay. Try this one first. So it shows oscillations, right? Why it feeds me with the error size. Oh yes, because yes, it was my bad, my error. It's not. It doesn't depend on x. It depends on time, and there should be a variable for time, which I don't remember, but we can. Okay, so we have so many units of time, and then it goes forwards and backwards. So the portion of the script in it may change if the script was modified, but this statement creates instantaneous value, and here this one accumulates more and more data point each time it comes through the cycle. Visualize any observable, done. Organization of data, bundling groups of observables. If one needs really high quality figures, it is always safer to redo them and manually modify line thickness, fonts, and stuff. It's very annoying when you submit a paper with your seemingly important discovery and it doesn't get to the editor. You get an answer from secretary of the editor telling, sorry, technical quality of your paper is substandard. Redo it and resubmit if you're interested. And so to avoid it, one needs to like this is substandard. The font should be like 10 times bigger, lines should be 3 times thicker. But for the research purposes, it makes sense to look on the whole picture on several observables or the same observable computer-based different methods at once. And the question in this talk is just on technical, mechanical part of how to do it. So in MATLAB, if you do plot x, comma, function 1, comma, x, comma, function 2, it will show 2 lines with function 1 and function 2. And then it makes sense to do so. If you need multi-panel, there is a special command. Let's identify where this image is done. So after we are done with main loop, there is so one opens new figure, and then there is a command subplot, which divides figure on multiple subplots, and then it is assumed to create array, two-dimensional array of subplots. The command here tells that there will be total subplots within one, total of 3 panels within one figure, and then it is column number 1, row number 1. So this subplot 311, which means we will be plotting the top figure. Then subplot 312 means that we will be doing mid figure. And then 313 means that we are doing the bottom one, right? And if, again, if projects will win over exams in your review votes, at a time of doing projects, there will be 2 stages. One, to do actual research and accumulate data for your personal understanding, and second, to generate high quality figures for the report. And for your own understanding, it just saves time to do this little pre-made figures. For final results, it's always better to redo them manually, at least to remove the gray background that you may have figured how to do, or you may figure it in the future. I believe one clicks on the arrow, double clicks there, and selects color white. Well, there are many little tricks, and the data can be saved into files and then plotted with your favorite plotter like Origin or Excel, but MATLAB gives competitive quality of figures. Okay, Anna, any questions about this subject? Okay, please, if you think that these discussions miss any information that you need for your presentations, send me an email. I will share more materials. I just do not want to flood the line with information that was not with unsolicited. Movies. I think this time it is the easiest, but it's we already voted for this, so it will stay here. So we just assign file, open channel, then we forward, we get frame, save frame into the channel and close the channel. And maybe you can remind this stuff to your audience and demonstrate a couple of figures for one or another situation with in different initial conditions or different potentials, just making sure that everyone feels confident. What are different potentials and different initial conditions? I read the question in your eyes. The different potential, it is what we all are going to do if we decide to do projects. Like here, one can define potential as anything you like, as a function of x. Instead of putting quadratic, you can put cubic, like x to the power 3, which is a little silly and useless, but any reasonable equation. What is means different initial conditions? Basically, you change p naught and x naught, so that the initial wave function will have different momentum and different position. So you explore different initial conditions for certain Hamiltonian, and do one of the things that are possible to fit within 4 or 5 minutes. Okay, any questions? Okay. In some sense, we already do 10 application wave packet code to harmonic oscillator. I can claim that I did it. So we've done eigenstates, dimensionalities, visualization, movies. Now let's see what else is missing. Numeric, Precis, modeling of quantum dynamics. We may have done it, right? It is the appearing and disappearing of wave packet on left and right.
Okay.
Okay. Maybe let me rerun the code by removing this quadratic potential, so returning back to the space. Yeah, here are the eigenstates of the free space, and somewhere there should be. Oh, it waits for me to hit. So right now, it probably doesn't have enough momentum to pass the border. So to do this exploration, I need to rerun the code with. Okay, no, it's partially covers. No, I will rerun so that it will show it more vividly. We increased initial condition for momentum, it goes more vividly, and I expect it to go once or twice through the border. To speak about this event, we may set up to derive an equation based on initial momentum, how many times the wave packet will pass through the border. Yes, I think that this is what I really wanted Wyatt to show. If I expand it, it's not as nice density of grid points, but one can look on it as going on a straight line and then continuing from the other side, right? And one can establish connection between initial momentum, the size of the box, I don't remember variable, but I will double check right now. And the maximal time. So basically, if you take mass times if you take your momentum p naught divided by mass and then divide it by, so it is actual velocity of divide over distance over time max, you compare you'll get how many times the wave packet will come through the border, and you may check if this equation gives fits well. So if it is if momentum is twice as bigger than the risk ratio, it will come twice. Triple, it will come 3 times. And then if you have the stripes going here and there multiple times through the border. White, would you be interested in able to do this little experiment?
The table part?
To rerun the code with different values of initial momentum,
Okay.
and plotting and showing this image until how many times the wave packet comes through the border, depending on the value of initial momentum.
I wouldn't really know how to do that.
Huh?
I wouldn't really know how to do that.
What do you mean? Can you run the code?
So we'll just run the code. Yeah, I can just
Run the code and copy paste this image.
Okay.
Copy paste the image that shows probability distribution, and do it several times for different values of initial momentum. Okay. Yeah. And if something is not clear, send me an email. It seems very doable, and I would be enthusiastic to contribute if needed. Okay. Size of simulation cell versus time of simulation. Norm. Okay, this is to some extent done. Let's double check the size of the simulation. So total time of simulation is n tau, number of time steps times tau. So 72 atomic units. If you look onto these trajectories, you see they run from 0 to about 72. So one can control how long or how short by setting up this number of time steps and duration of time step. Yeah, this thing is done in a very non-elegant way, but I apologize for it being not elegant. So there is a constant AZ about 6, then it's times 16, 6 times 16 will be like 96. And this is size of the box. So if you in atomic units, so if you look here, so it goes, bless you. The x-axis goes changes from 0 to 96, the variable L. And if we divide them one to another, one would get the velocity that is needed to pass the whole simulation cell within the duration of trajectory. Normalization of wave function in discrete representation. Initial wave function is normalized by doing this Gaussian wave function, and you get this normalization from our consideration of wave packet. But in addition, there is a chance of accumulating of numerical error during the simulation. And I believe in the middle of the code, there is an additional effort to make sure it's get normalized. Okay. So I'm inviting everyone to look onto the lines in my version is 284 to 288. So it relates to, well, I invite everyone to follow. It can relate again to a little bit to Anna, to Curtis, to Wyatt. So yes.
I wanted to ask why there are
Oh,
threes on everything. Why is it norm 3, psi 3?
thank you. I am very much appreciating feedback. There is an attempt to be organized. A lot of people, including myself, are failing in this, but I'm trying my best. So in this colloquial language for this code, method 1 is propagation in momentum space. Method 2 is defining momentum in coordinate space through Fourier transform. And method 3 is what we've got from James many years, I mean, many weeks ago. Wait, what was the question?
What was that?
Method 2 is when we through Fourier transform.
Oh.
Okay.
Oh, all right. To
So-
find the momentum.
Yes, yes. And when standard procedures like Hamiltonian, kinetic energy, expectation value of momentum are computed, there is an attempt to put a label that refers to by which method it was computed. So it's momentum's expectation value 3 means it is based on method 3. And we will, by whoever was brave enough to select commutation of operators, yes, we trust method 3 a little bit better than method 2. So if we need to choose, we select method 3.
Got it.
So let's focus on this little stuff. So what is written here? I'm just volunteering to write down, but I have no doubts that each of you is able to do it on your own. So expectation value of momentum is integral psi star, then you put actual operator for momentum. It can be literal, or I can just put dx, just put a p hat, then psi dx. So if I do have doubt that my partner gave me a good wave function, but I do not want to fail in my task, I can divide this stuff by normalization, which is integral psi star times psi dx. If wave function is properly normalized, it is not needed, but who knows? I just want to have a double safety cushion. So norm 3 is this little denominator. AP3 is average value of momentum by third method. So I do this psi times px3's operator psi divided by norm 3. And then if I want to keep it accumulating data from iteration to iteration, I just add it to average P3 array. So if I can do a little experiment and try to type what is the value of norm 3 and what is this average average P3. Norm 3. Well, it is 1. There was no reason for me to worry, but it's better to be on the safe side. Open a new figure and then plot average P3. So we have something strange, right? We see that along X, it is constant, and along Y, it is 10 to the minus 16. So it is a reflection that momentum, anything we do literally will have real and imaginary part. As we define momentum, it should be real, but through the procedure, and it for free space, it doesn't change over time. It's a constant. If you look for imaginary, it should be close to 0, but there is some numerical fluctuations. Okay, I already don't remember why I'm telling this, but normalization of wave function in discrete representation. Yes, it is for wide. Now, discrete representation of wave functions in space and in time. Well, I think that this is the main idea of the whole code, that we start at the very beginning. We start with discretization. We set number of points in space, number of points in time, and then we define the argument of wave function as number of points times increment in space. And then for time, we just have this tau is increment in time, and all our expectation values trajectories have a certain length, and they are discrete points. Why do you have questions? Many thanks. Okay. Spencer. Oh, Spencer. Accumulation of expectation values into array of data for the whole trajectory. I think we already did it. Let me retell this story once again. So I'm looking for the main loop. Then MATLAB editor has this little line that will go as long as the main loop is continuing, and where the line is ending, it is when main loop has stopped. Right? Is a way to navigate. And all these brackets are for accumulation of expectation values along the trajectory. Well, maybe something that no one else did focus on yet. Remember, you don't need to remember, but you may remember a little task that I personally gave to Wyatt to redo this figure over and over again for different I'm just looking for a way to rotate it for different values of momentum. So where this figure, which variable this figure is stored at, and how it is composed. So we do have.
Is there certain values you want me to put in for momentum?
Let's do it creatively. Let's find the value that gives. Try to find such values that let wave packet to go only half of the simulation cell, full pass through simulation cell, 2 passes from simulation cell, and I don't know,
Okay.
4 passes. That's it.
Sounds good.
And it doesn't need to be exactly, you just try a couple of values and then you report, okay, with this value, it passed through 2.5 times.
Yeah.
Good. So this figure that I've asked Wyatt to plot is stored in the variable S3. It is defined in here. The probe 3 is the one-dimensional array, right? It's probability distribution. Yes? And we do want to accumulate multiple instances of this probability distribution stacked one on top of each other. And we are doing it by taking the previous version of S3 variable, 3 probably for 3-dimensional, and then appending the raw vector at the end. And then it brings this 2-dimensional matrix where the value corresponds to the height. What to save? Let's check. Once upon a time, we were doing the. Does it do any saving? Oh, yes. So at least some variable it does save, but we can manually add if you need to replot any of the variables manually by different plotting tool. We can type what were we doing? So X is column, averages X3, yes, is also column, so we can do one column, another, it will be oh no, it should be time, not X. I'm doing the same error over again. Okay, so I defined X of t into new variable, and now I can do save scii, and somewhere else in the command line I can find this data. By the way, Garrett, there is traces from the past in your code, the file trajectory. If you do not save it in the same directory where is your code, the code will decline to work. There are a couple of places in the code which one can % out and then get everything fine, but to use it as is, one needs this stuff.
Okay.
So in MATLAB, I just created and saved this variable quadruple X. Then I open it in whatever editor, and you see this values of X, not values of time and values of the stuff, and I can open it in whatever plotter I prefer. I hate origin. What XXX using 1 versus 2 with line. I know it is not a big change. I replace one command line with another, but I like GNU plot because I was using it for my thesis 23 years ago. So it's an ancient. You see, it is the same dependence as you would get in the MATLAB. What? A second. AVGS3. So here is what MATLAB is doing, and here is what the third party software does. So we can export the data. Yes.
And that was the terminal command that you used?
You need to install GNU-plot through Brew or any to mimic Linux. You need to connect and install additional software, but or one can find online GNU-plot and then download and install.
Oh, okay.
What's the advantage over MATLAB? Or are you just showing us how case we?
I'm just it's a quickest
Okay.
thing.
Okay.
Why the following doesn't relate to the class. Why I love GNU-plot. The output of GNU-plot can be saved into the PostScript and PDF, and those right now no one opens these files by anything except Acrobat, but PostScript specifically and in some sense PDF are text files which are readable and editable. And GNU-plot generates this text format output that one can, if one needs to change one symbol and all data are lost, but you have this PostScript or PDF file, one can modify graphical information at the lowest level. What else? I just personally generated a lot of scripts in this GNU-plot sub language that speed up procedures, and it would take me time to redo them for other software.
Yeah,
but it is related to the subject of the class.
Is it an application you installed just off the web, or did you install it using the command line?
It works either way. It's so ancient, so free, and so it used to be so popular. Then you'll get it instantaneously from either one of sources.
Okay, I was about to say, because I was wondering if that was one of the things you could only find in a repository somewhere.
No. It's very public.
Okay.
And a lot of and another plus of GNU-plot. Now it looks like I'm a salesman. Everyone uses GNU-plot. Most of software that generates graphical information needs graphical terminals to observe what you generate. GNU-plot does not. You can blindly create graphical information, save them as files, and then download, upload them, and then watch them later. Why it is needed? Because supercomputers that two of you came on lab number 0 before we started, one communicates with supercomputers in the command line without graphical forwarding, and if one needs to quickly generate graphics without having a display, GNU-plot is the best friend.
That makes sense.
Okay. Emulation of expectation values into array of data. Done, right? Saving numerical data into files. Yes. Computation of expectation values, position, and momentum. I think we covered it. I can show it once again. The stuff here. Let me go backwards. Those 5 lines are for momentum, right? Because it finds expectation value of px3 that is defined earlier. If we have forgotten what is px3, we can just redo it. So mesh px3, it will likely show zeros because it is imaginary. And if you do imaginary part of px3, it will show the stuff that we discussed on previous meetings. So it is plus and minus on main subdiagonal and a couple of plus and minus on the opposite to help implementing periodic boundary conditions. And if we plug in this px3 into the quantum sandwich right here, we are getting the expectation value. So this is expectation value of momentum, and here is expectation value of position. In addition, this code does different like variances, which is root mean square deviation, right? They also accumulated for both position and momentum, and they are plotted because someone can be interested in them for uncertainty principle. And there is a set of variables that is pre-made to describe yield of chemical reactions. So this PL and PR is probability to the left, probability to the right. So X2 is midpoint of the x-axis, and one just adds together everything from beginning to the midpoint, and then everything from midpoint to X2. Or to the end of the stuff, and then one does this average PL3, average left and right of left and right. So if we decide to plot them, figure plot average P on left 3, it is, I think we discussed them. Time, comma, time, average PR3. Let me figure it out. So they're adding together gives 1, they're in opposite, and it is it shows 100% when the wave packet on the left part, 50-50 when it crosses the border, and then it switches when it is other. If in the future we will use our coordinate not as position of electron or length of a bond, but as a coordinate describing the progress of chemical reaction coordinate, we will use this PL and PR as the yield of the reaction. If the reaction went completely from left to the right, it means the reaction that has 100% yield. Expectation value of energy and uncertainty of position and momentum. Okay, so your task is not too hard, but it is a little lengthy. Let's cover it. Variance 3. So we subtract position and its expectation value, and then take square and find expectation value. So it's definition of root mean square, x minus expectation value of x squared times, we can put psi star here, psi dx integral, and it will be definition of the uncertainty of x, right? So it is in this version is line 262. variance. And then the variable variances 3, it just shows how this uncertainty progresses over time. Figure what variances 3. So originally it grows quadratically because we did run it for the free space, and then it goes discontinuity because half of the wave packet on the left, half is on the right, and then it continues growing on the same line, so it just deviates. Expectation value, uncertainty of momentum. For uncertainty of momentum, so we did uncertainty of position. Let's find uncertainty of momentum. I think it's this one, ASP3. So wave function third, wave function third, and then subtraction of momentum operator minus expectation value of momentum. So, and then it is accumulated in ASP. Yes, in the average SP3. So we do see that real component of average of momentum is basically a constant. You see it, there is a noise near 2.268, and the imaginary component is close to 0. So if we redo it for only real part, it will be something negligible in this close to certain value. When long time ago we were doing wave packet in free space as a homework, I don't remember 2 or 3, when we made expansion coefficients, we converted wave packet from coordinate space to momentum space. We had it as Gaussian function in terms of k variable, in terms of momentum. So, and it doesn't change over time. Distribution in momentum doesn't change. When we will be doing other systems, like harmonic oscillator or something more complicated, expectation value of momentum and its uncertainty will be changing in some interesting fashion. Expectation value of energy. Okay. If I have forgotten to do a little disclaimer. I do not guarantee that I'm saying too much exciting stuff. It is very natural to fall asleep. But towards your presentations on Friday, you may invest your time here, not to listening to me, but preparing your slides. And if your slides are already ready, then yes, sleep. How to prepare slides? Just run codes and make screenshots. So hopefully last thing for Spencer, expectation value of energy. It would be better to do this inside the loop, but here I was so confident in the energy conservation law that I placed this calculation outside of the loop. To check if energy conservation law is maintained, one should do it inside the loop and track expectation value of energy over time. So Hamiltonian, conjugated wave function, non-conjugated wave function, and the normalization. So if we type E3, it gives some value. Why it is interesting? There are at least two aspects. Who and why needs expectation value of energy? First, remember how we placed eigenstates of harmonic oscillator. We were offsetting them, right? When we will be doing more and more wave packets, to understand intuitively what is going on, it would be reasonable to offset wave packet on the vertical axis according to its energy. And the most natural way is not to tweak numbers by hand, but just add offset based on the energy, based on expectation value of the total energy. And then it will be, one would see that it will touch turning points and do some, will add some intuitive interpretation and understanding. Second, reason to compute expectation value of energy of Hamiltonian. We can practice classical expression for energy, and for especially for free space. This would be P naught squared divided by mass divided by 2. And interestingly, Hamiltonian has the same form, but their momentum is a quantum operator, and then we prepare a quantum sandwich. Here we just classically take the value, initial value of momentum as a parameter and take square. And you see results are different. Once we get 1.01, another we get 99. So the discrepancy between these two numbers is the one of the quantitative measures of quantum nature of the particle. So if the mass would be huge, wave packet will have very narrow width, they would agree perfectly. The more quantum features are involved, the bigger is this divergence. And the one of the examples that right now we are not talking about science, we're doing on protocols, how to run the code, but if we would, one of the most glowing examples, two glowing examples, if we would take energy of frozen harmonic oscillator in classical mechanics. The elongation from equilibrium is 0, kinetic energy is 0, total energy is 0, right? Classically. But from quantum point of view, we will find that even for the ground state wave function, energy will be non-zero. We didn't prove it in the class, but it will be 1/2 of the frequency times h bar. So there is 0-point energy. And a thing that we did before, particle in the box. The energy ground state of the particle in the box is non-zero. It is 1/L squared and some other concepts. So by assessing energy by through quantum and classical ways, we quantitatively assess level of importance of quantum theory for this particular situation. Done. Spencer, any questions? Okay, do not hesitate to send me emails. I love to read emails. I hate to answer them, but I will try my best to answer as quick as I can. And I have tons of materials, which I'll share if anyone requests. So I believe everything is covered. From my point of view, you're ready to prepare slides and present them perfectly. So we are done about 25 minutes earlier, but I'm about to announce, right? Yes, please do a favor and announce completion of the meeting, right? And if anyone has questions, I'll stay here and answer questions related to your presentations. But other than that, nothing or no one holds you to stay here. Feel free to depart, disconnect, disappear.
I'll email you.
Yeah, thank you, you too. Huh? Okay, perfect.
You're done.
Yeah.
Yeah.
You swing by. I'm not staying. I think I'm one.
You do.
Well, if I don't want to, then I don't.
Which
Is there a way to search characters in this?
Yeah. Yeah. Well, I found two checkers.
I've got the question, I do have an answer.
Oh, cool.
Thank you, Anna. This version of the code does not have the commands for making videos. But since you understand how the videos are generated, you can insert lines of the code into this
We know what-
here. And yes,
I don't know if I'll go there.
as so the initialization commands should be before main loop.
About this class?
Get frame
Like,
should be inside the main loop,
that's what the Bible stuff.
and the closing of the channel should be after the main loop.
I just.
Let's double check. Please find the end of the main loop.
Yeah.
We had like.
It will be a little line, vertical line here.
Yeah.
Yes, so before or after the pause, do get
Usually.
frame?
Before the pause?
Yeah, before or after, it doesn't matter. Yes.
And then the end will just be after.
Mhm, mhm,
Beginning.
mhm.
Okay. Perfect. Yes.
No. I in this version I forgotten to put it, but I trust they're big.
Yeah, big index, I'm like. Looks pretty big.
Font is big.
Yeah, oh boy.
Oh, is that the? What is that?
This is Patricia's code.
Oh, really? Did you run the full thing already?
I don't really know what I ran, I just.
It was 1,000 lines of code. How did you get so?
I don't know. M1 Pro, I guess.
Yeah. No, we have a shot.
But there's no animation. Actually, it might be doing the animation and just
Thank you.
file. I don't know.
Can you tell if your CPU is being used by this?
Oh, it's not. You can. I don't know how to do it on Mac.
Task manager?
That's not a thing.
Task manager, but for Mac?
Yeah, I don't know what that is though.
Task manager, I don't know. Is it performance monitor, resource monitor?
That sounds right. Resource monitor, yeah. No, that's Windows.
Parallels.
Yeah.
You have Windows on your computer?
It's kind of nice.
What the fuck did you put Windows on a Arc or,
It's called Parallel,
Arc machine?
Parallels Desktop. They're actually, Microsoft themselves came out and said they approved of Parallels because it's that good. So
Does
it's
it
pretty awesome.
run? So it runs Windows?
It runs